Good morning. We're going to talk today about how organic chemists represent and draw organic molecules. Okay, so you've probably seen molecules drawn like this before, whether that's at school or in a textbook. Now, these types of representations are incredibly helpful for those that are just beginning to learn chemistry. Okay, they introduce concepts that, for instance, that atoms can be bonded to one another, that, for instance, carbon can make 4 bonds, those sort of ideas. The trouble is there's a number of problems with this. Okay, most obvious of it is that they take a long time to draw, and for all but the simplest of molecules, they get very complicated very quickly. So overlapping hydrogens and overlapping carbons. Some other more fundamental problem is that for instance, that molecules have three-dimensional shape. So if we look at the three-dimensional shape of butane, which is the molecule that we should have drawn on the other page, we can see that if we have grey carbons and blue hydrogens, we can see that the molecule has a three-dimensional shape to it. This representation doesn't convey that information. Okay, it looks as though it's perfectly flat. It looks like every hydrogen is 90 degrees apart. Okay, which we know isn't the case. Okay. You've met in previous lectures that the carbon here is sp3 hybridized, and therefore it's tetrahedral in shape. So rather than being 90 degrees as the school type representation would suggest, the bond angles in here are closer to 109 degrees. Okay, so the molecule is bent. You can see this. The carbon atoms, because of this bent structure, adopt this sort of zigzag arrangement. Okay. So chemists need two things. They need a quick way that can convey information and looks easy to draw, and they need to be able to convey three-dimensional shape as well. Okay. Chemists use a system that's called line drawings or skeletal drawings. Okay. And I can quickly draw the molecule that we've got here, which is butane. Okay. And you'll see immediately what we've done is we've stripped off all the hydrogens, so the hydrogens aren't there, and we've not written out all the carbons. Okay. Instead, what we're left with is a zigzag line which represents the bonding between each of the carbon atoms. Okay. So if we flick back to our three-dimensional model again, here is the same zigzag line. We're now starting to represent a bit of that three-dimensional space and that zigzag. Okay. At every point, so here, and every inflection point, like here, we have a carbon atom. Okay. Every time we bend the chain, that's a carbon atom. Okay. Now, we can chemists know that carbon makes 4 bonds. So, what we know when we're looking at a molecule like this and a drawing like this is, well, if we look at this carbon atom here, we've only drawn 1 bond to it. That means we've got 3 bonds that aren't shown, and on that 3 bonds we have 3 hydrogens. Likewise, this position here, we have 2 bonds drawn to it. 1, 2. Okay, carbon makes 4 bonds, so that means we have 2 hydrogens on that position. Here, we've got carbon, and it's got 2 lines drawn to it, 2 bonds to it. That means this position here has 2 hydrogens. Okay. Finally, this endpoint here has 1 bond drawn to it. That means, because carbon has 4 bonds to it, that means there has to be 3 hydrogens to it. Okay, we compare this to the structure above. We find this carbon has 3 hydrogens to it. This carbon has 2 hydrogens to it. This carbon has 2 hydrogens to it, and this carbon has 3 hydrogens to it. Okay, so you're hopefully starting to see that we can actually build up and convey a lot of information in just a few lines, basically. Okay, let's extend this simple molecule, and let's start to convey a few other concepts. Okay. You've met that carbon can be bonded to other elements apart from hydrogen. Okay. We want to say attach carbon to chlorine. All we do is draw a line, it's a bond, and write the atomic symbol. So in this case for chlorine, Cl, and that's it, basically. If we are interested in including, for instance, oxygen in this chain, we can do that. Oxygen makes 2 bonds, so we make sure that oxygen now has 2 bonds going to it. This position here often confuses people, I'll be honest, but this is just a carbon and it's got 3 hydrogens attached. It's got this carbon to oxygen bond. That's 1 bond. We know carbon makes 4 bonds, so there's 3 hydrogens attached to this position. Okay. What we can also do is we can show multiple bonds. So for instance, a carbon-carbon double bond, all we do is we draw another line in. Okay. We can do the same thing for a triple bond, so single bond, triple bond, like that. And we can start to convey lots of information about the molecule in those sort of terms. So in this sort of molecule, this is ethine, okay, we have a carbon here and a carbon here. Okay, this carbon here has 3 bonds drawn to it, 1, 2, 3. That means that there's a hydrogen attached to this end, and I'm going to draw it in just so that you know that this hydrogen is here. Okay. Likewise, this carbon here has 3 bonds to it, 1, 2, 3, and there's a hydrogen attached to that end. So we're building up from with these simple lines quite a lot of structural complexity in the organic molecules that we can draw. Okay, there's one thing that we've not talked about yet, and that's our 3-dimensional space issues. So here is our butane chain again, and let's say, for instance, that we're going to put a chlorine atom coming off of this atom here. Okay, chlorine's now shown in green. Okay, you'll see that the chlorine atom is now sticking out towards us. Okay, the hydrogen's behind, and we've got this methyl group CH3 to the left, and we've got this ethyl group CH2 to the right. Okay. How do we draw that? Okay, well, that's fairly straightforward. So if we draw our butane chain again, okay, so here's our butane chain. Okay, and we have a chlorine atom which is coming off of this atom here, and that's coming towards us. So the way we show things coming towards us is with a solid wedge. Okay, it's a solid bond, and then we can attach, just write the element symbol to that. Okay, so solid wedge means something's coming towards us. Okay. If something's going away from us, so let's say for instance we now have a fluorine, Okay. This fluorine is going away from us. And we've drawn that using this dashed wedge now. So we've had a solid wedge for coming towards us, and we've got this dashed wedge for going away from us. Okay. Right. So we've now got, we've introduced the idea that we could draw a zigzag chain to show a carbon chain. We can introduce elements by writing their atomic symbol. We can draw multiple bonds between elements, and we can now introduce three-dimensional space using these solid and dashed wedges. Okay, let's look at a more complicated example to pull all these concepts together. Okay. Here's a compound called biotin. It's a vitamin, and it's incredibly important to individuals' health. Now, what we have here at the centre is we have this carbon chain, okay, shown by this zigzag chain. Okay. We look at this carbon atom here. This carbon atom has a single bond to this oxygen on the right, and a double bond to this oxygen here. Okay. This functional group is called the carboxylic acid, and you'll meet that in later lectures. Okay. We'll see that this carbon atom here is coming towards us. Okay, we've got a solid wedge here, and that means it's coming out of the page towards us. This dashed wedge shows that this hydrogen here is going behind the page that we're looking at. Okay, so it's going away from us. Okay. We can count the number of hydrogens we have. So on this position here, for instance, we have 2 bonds that we can see. Carbon makes 4 bonds, so that means we have 2 hydrogens that we can't see, that aren't shown, just for clarity. Okay. Likewise, here, this carbon atom has 1, 2, 3, 4 bonds to it. That means in this position there are no hydrogens. Okay. Okay. So we've gone from simple alkane, butane, up to quite a complicated vitamin. You'll see that we're drawing on the same lessons. Okay. Let's just go the other way and quickly interpret a molecule, and from just its drawing we're going to work out what its molecular formula is. Okay, so I'm just going to draw a random molecule. Okay. And what we are going to do is we are going to count all the carbons and all the hydrogens and all the oxygens, and we're going to get a molecular formula for this molecule. Okay. Right. Okay, this is a completely random molecule, probably wouldn't exist. And we're just going to count everything up. Okay, and we'll do the simple things first. Okay, so we have 1 chlorine. Okay, that's here, the Cl group. We have 1 oxygen here, and we have 1 nitrogen. Okay, now we're going to count number of carbons. Okay, so we're going to start here and go 1, 2, 3, 4, 5, 6, 7 carbons. Okay, now we're going to count the number of hydrogens. Okay, and I'm going to annotate this diagram as we're going, just so that we don't forget where we are. So this position here, this carbon here, has 1 bond drawn to it, so that means it's got 3 hydrogens attached to it. Oxygen has a hydrogen attached to it, so that's one hydrogen. Okay, this carbon here has 4 bonds to it, therefore it's got no hydrogens on it. This carbon has 1, 2, 3, 4 bonds to it. Remember, this is a double bond, so there's 2 bonds there. So that's 0 hydrogens there. This carbon here, on the other hand, has 2 hydrogens attached to it. It's got 2 bonds drawn to it. Remember, carbon makes 4 bonds, so that means we've got 2 hydrogens. This bond here, this carbon here, has 3 bonds drawn to it, that, and this double bond, that means it has 1 hydrogen drawn to it. This carbon has 2 hydrogens bonded to it. This carbon has 2 hydrogens. And let's not forget the nitrogen, which has 1 hydrogen. Okay. Okay. All we need to do now is add these up. Okay. So we have 1, 4, 5, 7, 8, 10, 12 hydrogens. Okay, so we're just going to write out its molecular formulae, and we have C7, H12, NOCl. Okay, remember that the number of atoms gets shown as subscript. Leave us with our molecular formulae. Okay, so we've gone from a structure that we've not met before, and we've been able to work out its molecular formulae. And from that we can calculate other things, for instance its molecular weight. Okay. So hopefully you've seen that the drawing organic molecules isn't actually that difficult, that the ideas and concepts are fairly straightforward, and the thing that will tricks most people when they first start is counting the number of hydrogens. Okay, carbon makes 4 bonds. Count the number of bonds to the carbon and you'll be able to work out the number of hydrogens.